Our team would like to present to you our EGR 305 Advanced CATIA Final Project, a full assembly of the lunar lander. This project consists of 4 members, JD Barnett, Tucker Hawkinson, myself, Yessenia Lopez, and Billy Nguyen. Our proposal changed throughout the course of the project, but our base proposal consisted of 4 sub-assemblies, including the landing legs, which used DMU kinematics, our fuel tanks and our engine, which should have used sheet metal and advanced GSD, our antenna and our docking port, which used DMU kinematics, and the structural component of the inside of the fuselage, which holds the fuel tanks together, which was consisted of sheet metal and advanced GSD. Our full assembly from our lander, as you can tell, is a little different from our proposed assembly. This assembly consists of a high gain antenna on the side of the fuselage, along with 4 landing gear instead of 3. Our engine was a little larger as well once we came down to the dimensions, and our docking port, instead of protruding out to the outside as in a proposed assembly, it actually went in to our fuselage body. In this slide, you could see our exploded view from our lunar lander. As you could tell, the lunar lander had several major components within itself, such as the fuel tanks and the engines were constructed as one assembly, and then we have here a rib cage that goes inside the fuselage, which helped hold together the fuel tank and the engine. This gives you a better idea of all of our components which created the overall lunar lander.
Hi, I'm JD Barnett, and I was responsible for the propulsion system of the lunar lander, which is the fuel tanks and the engine. Starting with the fuel tanks, as you can see here, pretty straightforward, but pay attention to the pipes and the isometric because that's where things got a little bit interesting. As far as building the model, most of it was pretty straightforward. Just a shaft command for the upper tank, a shaft command for the lower tank, and the pipes were just done with a couple of rib commands. I'll get to why they needed a couple of rib commands in a minute, but as you can see, the pipes are a little bit offset at top and they come back together at the bottom. The only challenging thing here really was the pipes, because they were offset in the area between the tanks, and then I wanted them to come back to the same point on the bottom. So I ended up needing an additional plane aside from the usual X, Y, Y, Z, and XZ. So I had to create about a 20-degree offset plane that allowed both pipes, to come back together at the bottom and end up both going smoothly into the combustion chamber of the engine. Now we have the engine, which you can see here is a hollow for throughout the entire thing. Again, pretty simple and straightforward, just a shaft command with a little bit of an interesting profile. There were lots of corner commands, which I'll explain in the next slide. And this box is what I started with in order to make sure that the engine fit inside of the dimensions I was given. As far as the challenges for the engine, I was starting from scratch. I really didn't have much of an idea of what a lunar lander engine was supposed to look like, so I had to look up some other engines for reference. The engine needed to fit certain dimensions so it would fit inside the structure and be compatible with everyone else's parts. And then I mentioned before that there were lots of corner commands, and that's because I didn't want any hard edges to be anywhere on the inside of the engine to negatively affect the flow of the fuel and then the exhaust. So everything is rounded so that that flow would be smoother. And then as far as the material, it was actually a little bit harder than I expected to figure out exactly what material the nozzle of an engine is made out of. Obviously you need something with a very high heat resistance that won't melt or deform.
Hi there, my name is Tucker Hawkinson, and I will be talking about the landing legs portion of the lunar lander. So on the left, as you can see on the screen right now, there is a image of the collapsed landing legs, and on the right is an image of the expanded landing legs. And this is, I'll talk about the way that these were made later, but this is the final product of using the kinematics toolbox. So let's talk a little bit about building the model. I used the DMU kinematics toolbox, and I first started with the mounting points. The first one that was put in there was this upper one, and that entire rod is one piece, and it was fixed. And that was the first part in there, followed by this cylinder piece, and then followed by all of these center pieces. So these were the biggest challenge, and I'll get to the challenges a little bit later. But these were the biggest challenge in getting this thing together. There were 3 main subassemblies that were imported, and I'll also talk about those a little more in depth later. But the major kinematic joints that were applied were a revolute right here, which is the driving joint. There was a cylinder. There were many cylindrical joints in here. The prismatic joints is the one that allows us to slide back and forth inside here. Again, there were many planar joints in here, and then there were a couple of rigid joints, especially relating to this piece right here, to the fixed piece. So the 3 main subassemblies were the center slider piece, the lower cylinder with the ball, and the pillow block. The pillow block was the main subassembly that really made sense to be a subassembly, but these 2 were made to be subassemblies because of the DMU kinematics toolbox. This toolbox is all about the degrees of freedom. So when you add these balls in here as the spherical joints in there, it actually ends up adding 3 degrees of freedom. And what we needed to do is we needed to bring that down. So if you add it into this subassembly, it ends up bringing it down to 2, which is a little more manageable when you have a few balls in there. So both of these were to bring that rotational degree of freedom away. And then I also worked on the sort of an advanced flyby animation, which is this one right here. So you can see that not only when I play this, you're gonna see that not only is the thing expanding, but the viewport is rotating around as well. So this is a good example of, if you were trying to show how an engine worked, this may be a good flyover tool. And you can see down here I start to focus down on this piece. So a couple of the biggest challenges. One of the challenges was there were only really general dimensions for this. There were no hard mounting points. There was really no points for me to work off of to start. And I found that it was a lot harder to start with a completely blank slate than it would have been if I had a couple of points, even just 1 point with a couple of dimensions of how big the footprint needed to be. That was a little tricky right at the beginning, but that one was just one that I ended up pushing through and getting to the point where I gave myself those. The second thing is a slight dimension miscommunication, which caused the landing legs to be scaled slightly smaller than the rest of the lander. It's still works, but it's not quite to the spec that we were hoping for. And the final thing that was the hardest part was the kinematics. The biggest challenge was was to find the missing degrees of freedom. As I said before, spherical mates add 3 degrees of freedom to the model, and you can bring that down to 2 if you add subassemblies with the balls already placed in them, but you still have to figure out where all your degrees of freedom are. And on a model that's got 8 to 10 parts, that each time you add a piece in there, it adds 6 degrees of freedom. So you have to define all of those before it'll play.
This here is an image of the antenna. It is composed of a high gain antenna, which is the big disc, a low gain antenna, which is standing up top, a spherical shape, and then a base. As you can tell, the antenna is meant to rotate in both the X and the Y direction, and you'll be able to see more in a. Here you can see a better representation of what the antenna actually does. As you can see from here, it is rotating on the X direction, and then it rotates on the Y direction. This is done through a spherical joint. The antenna was built using all parts were individually made. So the dish that you saw previously was made by itself, the LGA supports, which was a low gain antenna, the base, and the sphere. The kinematics used were spherical, revolute, and rigid, and DMU fitting was used to create the simulation with the sequence and perform the sequence in order. The antenna's kinematics consisted of a spherical joint, which was added to the base of the sphere and the sphere. This created a revolution about the z-axis, and it created 3 degrees of freedom. In order to remove these 3 degrees of freedom, we had to add a revolute joint that was added from the high gain antenna to the sphere and the base using the YZ plane in order for it to rotate around the x-axis, and the same had to be done with the ZX plane in order to rotate about the y-axis. In order to get rid of the 3rd degree of freedom, we had to use a rigid joint between the high gain antenna and the sphere, because every time that the animation was played, the sphere would rotate, but the antenna would stay intact. So when we created a rigid body, it got rid of the 3rd degree of freedom, and the plate would rotate along with the sphere. Some challenges that came upon with the antenna was the dimensioning of the antenna, since there were several internal structure that was very small, and we didn't know much about the sizing of the lander. Some of the parabolic shapes interfered with the dish, and then interfered with the lander. The kinematics were also a very big challenge, since I've never used experience with kinematics. I didn't really know what to expect. We used the one spherical joint, which created the 3 degrees of freedom, which were difficult to actually pinpoint out, and thanks to Professor Gribbins, we were actually able to, she helped me realize that we needed a revolute joint and a rigid joint. And as I explained before, the revolute joint was added in order to make the rotation of the antenna in the Y and the X direction, but this had to be a little more intricate. We had to add a line between several components, from the high gain antenna to the sphere, and then the sphere to the base, in order for it to actually get the lines and the planes in order to produce the revolute joint. Another problem when recording this, having the correct angle of rotation for the simulations, along with running 2 different simulations at once, was a little more difficult than expected. Having the correct speeds and the proper angles was somewhat challenging, but overall it was able to produce a working antenna. The docking port was another tedious process. It was originally going to be a little more intricate, but due to my lack of experience with kinematics, I decided to narrow it down. As you can tell from here, this is the docking port when it's compressed, and here is when it's extended. The docking port mechanism, as seen here, extends to the outside, and then it rotates. This allows for the port to actually, whenever it's docking onto the Deep Space Gateway or the International Space Station, this allows it for it to actually interact with the assembly, and I'll show it again. You could see it coming up. This would be extending and reaching on, and then the circling or the looping would be for it to actually connect and contract back to create a perfect seal with the docking station from another, like I said before, the ISS or the DSG. The docking port was built with two separate parts, the port base, which was the rigid base that stayed intact, and the docking extension, which was the actual part that extended and rotated. The DMU kinematics that was used were just a cylindrical joint. The cylindrical joint had a angle of freedom and an angle of distance of length, which created a zero, which helped create the 0 degrees of freedom, or else originally we had 2 degrees of freedom. And then the DMU fitting again was used to create the simulation like seen previously, the sequence and the recorded sequence. The docking port's kinematics, this docking port had to extend a proper length in order for it to still be attached to the base. This docking port here had to extend the same length as the base, or else it would be free floating, and that is impossible. Along with that, it had to rotate in order to latch on to the docking port of whatever it is docking onto. Therefore, a cylindrical joint with an angle and length driven limits were created. The extension had to do a 360-degree rotation, and this degree was set here with the angle driven, while the length driven had to adequately lift up and extend the internal portion the same length of this part here, which you could be seen on this side. The docking port challenges, although it was only 2 parts, both parts had several intricacies to it. Originally, the docking port was meant to have some more intricate parts, but due to some last-minute errors and time crunch, the port was simplified. Originally, it had to extend with a piston and with a set of piston and coils, such like a spring, but instead we just created it with like a sliding rotation, a cylindrical rotation, which was easier to process.
The skin of the probe was made in generative sheet metal design, and as you can tell by the shape, it's very simple. It's just a plain old cylinder with a very thin thickness, and the material is made out of aluminum. So using generative sheet metal design, I first drew a circle that had the radius of the base frame of the fuselage for the probe, and then I proceeded to extrude it the height of the fuselage with the rib section. This will be shown in the next couple of slides when you see the overall structure of the fuselage. It is worth noting though that because this is generative sheet metal, there is no physical geometry to constrain to, so I was forced to use the cylindrical constraint. It kind of looks like this in the CATIA workbench, if I can draw it with a mouse. Kind of looks like that, and I basically had sort of an offset constraint using the planes. Aside from that, this is a very simple part that was made in generative sheet metal design. Unfortunately, this is the only quote-unquote advanced part that I made with a design bench other than the general tools that we've been using in CATIA so far. The internal structure of the probe consists of 3 main parts. The first part being the cap, the second part being the fuselage, and the third part being the base. Now, when the project was originally pitched to all of us, dimensions and even drawings for the entire spacecraft itself did not exist. So, as the project progressed, design features like this platform for the antenna to be mounted to, this hole for the docking port, and these landing gear support pieces were later included so that all of the parts were able to be constrained to the main body of this fuselage. And this is very important because a majority of this assembly is curved, and CATIA will not let you constrain to curved surfaces unless you either use an offset constraint or you create fake geometry, or even creating physical geometry with flat surfaces, which was the purpose of this piece and this piece. Despite being only 3 pieces, this assembly was very, very complicated and challenging to put together. Some of the challenges I faced included not knowing exactly what the final dimensions of my parts would be up until my teammates submitted me their parts. For instance, if you look at the base, these extruded points were created so that the struts of Tucker's landing gear had a hard point to attach to, since, as mentioned in the previous slide, curved geometry in CATIA could not be constrained to. Another example is this circle here. This extruded circle was created so that Yesenia's satellite dish could mount to the side of the fuselage, and in addition, this hole was cut out so that Yesenia's docking port could sit on the top of the spacecraft. Additionally, at the very beginning of the project, dimension drawings did not exist for the entire spacecraft as a whole. The only thing that was provided to us was a maximum diameter and height for both the fuselage and the fuel tanks. As time progressed and as more parts were made, the spacecraft assembly, or at least my assembly, started to take shape after thoroughly investigating all of the needs and requirements of what a potential spacecraft of this design could need. Another challenge I face, as mentioned before, is that I did not use any complex workbenches to assemble or create any of these parts. And that is simply because there was no time, nor was there any need to use advanced workbenches beyond part design to create any of these geometries. As pointed out by several team members, a lot of the dimensions that I've used for bolts, for instance, are not realistic. Also, too, this ribbed structure was designed with aesthetic purposes in mind without actually researching what kind of internal support structures are used in today's spacecraft.
Finally, for the team dynamics, we tried to break everything down as fairly as possible. There were 4 main parts to the structure, so each group member took one. As you heard in the video, Tucker Hawkinson did the landing legs, Yessenia Lopez did the antenna and the docking port, Billy Nguyen did the skin and the internal structures, and I, J.D. Barnett, did the fuel tanks and the engine. For the presentation, as you could tell, each person did the individual slides for their parts, and any other additional aspects we just put evenly, including the exploded views, the overall structure, and the team dynamics this slide. For the report, we all worked together, made sure everything we did was included, and that no one person was doing too much of the work. Thank you, and that was our presentation on our lunar lander.